Share screen, the usual thing here tonight, as we normally do. Let's see here. Oh, I need to click this. All right, let me collapse this here. Collapse that. Okay, good. Let me get this share screen. Let me turn this on so it makes a difference. All right, we'll try to lock this in. All right, ladies and gentlemen, this is the summary sheet from Tuesday's lecture. So let me go over it quickly. We were dealing with the emission and absorption of radiation. For simplicity, just from a single electron atom. We write the Hamiltonian as a sum of three terms, H0, H1 plus H2. The H0 consists of the usual Hamiltonian for the electron. Here it is. You can think of hydrogen as just fine. This is easily generalized to other material systems, and we're considering a single electron atom just for simplicity. But there's also the Hamiltonian for the free electromagnetic field. The matter and the field are not coupled by H0, so they just evolve independently as far as H0 is concerned. Perturbation H1, however, does couple the degrees of freedom. It has two terms. There's a P dot A, which comes clearly from the expansion of the kinetic energy in K0. It's the cross term. There's also an S dot B, which came from the interaction of the spin of the particle with the magnetic field. Unlike the applications we've had earlier in this course, however, the fields A and B are quantum fields now. They depend not only on the particle position, electron position in this case, which is the vector R, but they also depend on the creation and annihilation operators for the field. And then at second order, there's a term that goes as A squared that comes from the quadratic term and the expansion of the kinetic energy. Now then, it turns out that in problems like this is that carrying out a perturbation expansion and powers of the fields, here it's A and B at first order and A squared at second order, develops quantities we're interested in, such as transition rates and cross sections and so on, as a power series in the fine structure constant. And so to carry things to lowest order, we're going to just use first order time-dependent perturbation theory and concentrate on H1 and ignore H2. Now we did that for the case of spontaneous emission and got this result here. So let me explain that a little bit, remind you of it a little bit. We have it's gotten kind of in the way of my buttons here. We have two states, atomic states, an upper and a lower, B and A. We assume that initially the atom is in state B, but it emits a photon and drops into the lower state A, which might be the ground state, but it just has to be some lower state. We then use the quantized theory of the electromagnetic field to derive the expression for the differential transition rate. This is the rate W per unit solid angle per time for a given polarization mu of the outgoing photon. And it's expressed in terms of a bunch of factors here that you see here, times the square of a certain matrix element, which I call MBA. Now, every time I write down MBA, I think about the degree that you might have gotten instead of a PhD in physics. But trying to make a joke by Zoom doesn't work very well because nobody can laugh. Anyway, this is good, thank you. So this is MBA. The B and A refer to as you can see, they refer to the initial and final states, as you see from the diagram here. And this is the matrix element in question that comes out of the theory. The operators P, momentum P, spin S, position vector R, all refer to the electron. So when you take the matrix element between states A and B, they disappear. What remains is the K and the epsilon, which are effectively descriptions of the mode of the photon. So this matrix element MBA depends, as you can see if I pull it over, it depends on the two atomic states B and A, as well as in the mode of the outgoing photon, the K vector and epsilon. Now the magnitude of the K vector is determined by energy conservation, but its direction is a free parameter, and so that's something to keep in mind about this dependence. All right, in any case, this is what we get for the differential transition rate. Now then, integrating this over all solid angles and summing over all polarizations mu, the solid angle omega, by the way, refers to the direction of the outgoing photon. So it's really in the K space of the photon. In any case, and integrating also, summing over the polarizations, gives us the total transition rate, which I just write as W, except people oftentimes write that as the Einstein A coefficient, which I denote by A sub E, where E stands for Einstein. The Einstein A coefficient is just by definition, it's the rate of the total rate of spontaneous emission. And it can be expressed in terms of a certain average, which is what this overbar means, of the square of this matrix element. The differential transition rate has the square of the matrix element, but not averaged. In any case, the average is defined as 1/4 pi times the integral over solid angles times 1/2 the integral over, the sum over polarizations of the unaveraged square of the matrix element. Again, the omega here refers to the k vector of the outgoing photon, so it's in k space is where that omega is. All right, now then, so that takes care of spontaneous emission. We also studied the process of absorption. Absorption is kind of the reverse process. This is where the atom is initially in the lower state A, absorbs a photon and gets lifted into state B. Now the atom can't do that unless in the initial state contains photons in the field. So we assumed initially that there was some occupation number basis state in the initial state, although later on we replaced that with a statistical description in which all we know is the average number of photons in the various modes in the initial state. In any case, we obtain an expression, again, by straightforward time-dependent perturbation theory, we obtain an expression for the total rate of absorption, and it has some factors in front, sum over polarizations, integral over solid angles. That's just summing over all the possible modes of the photon which has been absorbed from the incident field. Then we've got in here the average number of photons in a given mode k and epsilon multiplied by the same square matrix element that occurred in the rate of spontaneous emission. Now, in general, it's kind of hard to do something with this sum and integral here, but in the special case in which the radiation is isotropic and unpolarized, that means that the number of photons in a mode is independent of the polarization and also independent of the direction of k. Therefore, it depends only on the magnitude of k, or equivalently on the frequency omega. So for unpolarized isotropic radiation, the average value in lambda actually depends only on omega. If that's the case, then this quantity can be taken out of the sum and the integral, and what's left over is essentially the average of that square matrix element again. And this allows us then, in the case of isotropic and unpolarized radiation, to express the total rate of absorption in terms of the total rate of spontaneous emission, or in other words, the Einstein A coefficient. And so to summarize some of those results, what we find is that the rate of absorption is proportional to the Einstein A coefficient, and the proportionality is the average value of the number of, which is a function of frequency here, of the number of photons in mode lambda. Turns out this can also be written as something proportional to the energy density in the field, in the incident field, energy per unit volume per unit frequency interval, times the coefficient, which by definition, we just write as B sub E. By definition, that's the Einstein B coefficient. And the result of our calculation is a proportionality between these two with the coefficients that we worked out, and here they are. So this is kind of the setup of or derivation of the Einstein A and B formalism based on quantum electrodynamics. Now, in your undergraduate course, you may well have derived the total rate, the Einstein A coefficient. You may well have derived this formula or something equivalent to it using what's called the semi-classical theory of radiation. This is, in my opinion, a rather ugly theory, and I'm not teaching it in this course. I don't like it. And in fact, the use of that theory to derive this Einstein A coefficient is a rather convoluted and complicated theory. But it kind of goes like this. Is what you do is you have an atom and you assume it's interacting with a classical light wave or an ensemble of light waves. And then from that, you can compute the absorption rate. You can show that you can show then that if the ensemble of light waves has random phases, and if it's isotropic and unpolarized, then you can show that the absorption rate is proportional to du d omega, and therefore you get the Einstein B coefficient, B sub E, like this. On the other hand, by setting up a kinetic equation, assuming radiation is black body radiation, a special example of isotropic and unpolarized radiation. You can solve the kinetic equation using the Boltzmann assumption about the population of the atomic energy levels, and you can find a relationship between the Einstein A and B coefficients. Therefore, knowing the B coefficient, you can solve for AE, and that's how you do it typically in elementary treatments of this subject in which you don't want to quantize, or you prefer not to quantize the field. In any case, that's how it's normally done. Notice that by using quantum electrodynamics, we get not only the total transition rate A sub E, but we get its detailed resolution into angles and polarization of outgoing photons. We get much more information than we got by the semi-classical theory of radiation. All right, now that's kind of a summary of what we did last time. And the first topic I'd like to take up tonight is a brief overview of a third process, which is that of not spontaneous emission, but rather a stimulated emission. So let me put this aside. So I want to talk about stimulated emission. So stimulated emission is the basic idea is this, is that it's similar to the process of emission in the sense that we have an upper state A for our atom and, upper state B for the atom and a lower state A, and it emits a photon dropping into the lower state, which goes out into mode lambda. The difference is that we assume that the photon field for the initial state is not empty, but rather contains a collection of photons in different modes. Initially, we can make this into an occupation number eigenstate. And if lambda is the mode into which the outgoing photon goes, then in state A, after you've dropped to the ground state, the number of photons in that one mode has increased by 1. So you get a setup like this. It's then completely straightforward to carry out the time-dependent perturbation theory and to derive the formula for, let's call it the total rate of emission, the total emission rate. And here's what you find. You find that it's the average number of photons in mode lambda, which for isotropic unpolarized radiation is a function only of the frequency. That's in the initial photon wave field, like this, plus 1 multiplied times the Einstein A coefficient, A sub E. Now, the 1 times the A sub E is the rate of spontaneous emission. So this 1 here is the spontaneous rate. On the other hand, the average of n lambda of omega times A sub E, I didn't belabor this, but this is something we derived in the last lecture. That's equal to the rate of absorption. So this term here is the rate of absorption, W absorption. Well, by definition, we say that this is also the rate of what we call spontaneous emission. We call it, it's not spontaneous. It's stimulated emission. Let me get it right. This term is called the rate of stimulated emission. Why do we call it that? It's just a definition. It's the same as the rate of absorption by the calculation, but why do we call it the rate of stimulated emission? The reason is that it's proportional. It's what it's saying is that the probability of making a transition into mode lambda is proportional to the number of photons that are already in mode lambda. So in effect, the transition has been stimulated by the presence of photons that are already in that mode. This has a simple classical interpretation, because if you have an atom in an excited state, and you send in a light wave, which has the same frequency as the transition frequency to a lower state, that light wave will shake the atom at its resonant frequency, and therefore induce transitions and make them go faster, make transitions to its lower state more quickly than it would have been on its own, which is just the spontaneous part. So this part is the part that's stimulated by the light wave, which is already in the field, and that's what this in lambda distribution of occupation numbers in the initial state is all about. So that's called stimulated. So we can say that the total rate of emission is the rate of stimulated emission plus the rate of spontaneous emission. Now I'm omitting other details about this, but this is the basic idea. By the way, the reason we get this n lambda plus 1 is because in this case of emission, unlike the case of absorption, we need to apply a creation operator to our system that has to the initial state like this. In the analysis, you have a creation operator like this, and this gives rise, according to the usual rules for harmonic oscillators, of the square root of n lambda plus 1, and that goes into the matrix element. And when you square that to get the transition rate, that's where you get this n lambda plus 1 factor that appears here. So the 1 that appears here, which represents a spontaneous emission, is the funny one which is ultimately related to the commutation relations of the creation and annihilation operators. All of this is important in the theory of lasers. The fact of this in lambda, which appears here, the stimulated emission part, is the basic idea that underlies the mechanism for amplification in the laser. The idea is that the modes that already have photons in them are the ones that are most likely to receive the photons from the atom making its transition. Now, the total rate, of course, depends on other things besides n lambda. The AE contains matrix elements in there, and there's a question of the energy of the outgoing photon. But at least insofar as the influence of this factor is concerned, the n lambda is here, and it tells us that the modes that already have photons, it's kind of like capitalism. The people that have money are the people that keep getting more money, and this is how it works also in the case of stimulated emission. So if you have, let's say, a laser cavity in which there's only one mode or a small number of modes that are occupied by a large number of photons, then those are the modes that are most likely to receive new photons that are created when atoms make their transitions from the upper state to the lower state. In saying all this, however, we have to recognize that this rate of stimulated emission is also the rate of absorption. They're equal to one another. So if you've got atoms in the lower state, they're going to be making transitions back to the B state. In other words, the field makes transitions, forces transitions both ways, up and down, like this. The only thing that's independent of that is the spontaneous emission, which is strictly down from the upper state to the lower state. So in order to get amplification, it's necessary to have a population inversion. That is to say, to have more atoms in the upper state than you do in the lower state. That's what you do. You pump your medium first to get that, and then you send in a probe wave that then gets amplified. That's how it works. But you have to have this population inversion, otherwise it would go the wrong way. In particular, in thermal equilibrium, the upper energy state will have fewer states occupied than the lower one. The Boltzmann factor determines the difference, but it'll always be less than if the energy is greater. So having a population inversion is a non-equilibrium situation, and that's where the energy comes from to derive the amplification. The +1 that appears here, by the way, the spontaneous emission, doesn't help your laser at all, because this is the same one for all modes, and thus this represents atoms making transitions in any mode it wants. It's of course governed by the AE as well, but except for that, it goes in any mode it wants. So you're going to have photons coming out sideways and things like that aren't what you want. All right, so that's a little bit of a brief overview of the field of spontaneous emission and how it fits into laser physics. Now, at this point, what I'd like to do, maybe what I should do first is just ask if there's any questions before I go on. This is so far, it's just really mostly an overview of what we did in last lecture. All right, if no questions, then I'll move on. The next thing to do is, I think, examine in more detail the most interesting example of these three processes, which is the case of spontaneous emission. As I just explained earlier, this is difficult to derive by the semi-classical theory of radiation, which I don't cover in this course. But in quantum electrodynamics, it's probably the simplest result you can obtain. It's clear that things depend greatly on the square of this matrix element. If you want to know details about how things depend on angle and polarization, that's where it lies. It's in this MBA. So let's turn now to analyzing this matrix element MBA. By the way, the I over H bar here has no significance, really. It's just a conventional factor. Just makes a definition we can use. But anyway, let's look at that. Now then, so let's look at the MBA. Now, the first thing, let me bring it back again. The first thing to point out is that the different quantities that we see in here have different orders of magnitude. I'm going to use a hydrogen atom near the ground state with quantum numbers close to the ground state as a reference system in order to estimate orders of magnitudes of various quantities. In the notes, I also include the Z dependence, which allows for other single electron atoms, and with other modifications, you can use it to cover other circumstances. But I think this is a good place to begin, just to have a reference that we can talk about. So in the ground state of hydrogen, it's convenient to analyze things in atomic units, because if we do, the H bar is 1, the momentum is of order unity because it's near the ground state. The spin is H bar over 2, which is basically of order 1. The polarization vector is a unit vector. It's of order 1 also. The position vector R is, of course, a variable of integration in the matrix elements, But if the states A and B are reasonably close to the ground state, then their spatial extent is basically the Bohr radius. So this R here is cut off at the Bohr radius. And that means that that's also of order 1 in atomic units. The thing which is not of order 1 is the wave vector k, which is the wave vector of the photon. So let's analyze that. Here, let me analyze that. So the wave vector k, if I just leave the vector sign off, this is of course equal to the frequency omega divided by the speed of light. Now in atomic units, the frequency omega is of order unity. The reason is that this is of course the Einstein frequency connecting the two atomic states between which you're making a transition. But that frequency is comparable to the orbital frequency of one or the other of the two states, maybe the average of the two. That's the general idea of the order of magnitude of it. It's comparable to the orbital frequency of the electron around the nucleus. And in atomic units, that's of order unity. That's what it is for the ground state. The c, on the other hand, the speed of light in atomic units is equal to 1 over alpha, where alpha is a fine structure constant, and so that's large. And so what we see is that an order of magnitude k is equal to alpha, which is therefore much less than 1 in atomic units. It's a small quantity. This means in particular that k dotted into r, which we see in the exponent of the light wave, is also of order alpha. This is equivalent to saying that since k is 1 over lambda, this is equivalent to saying that r divided by lambda, where r is the size of the atom basically, and lambda is the wavelength of light, is of order alpha, which is therefore much less than 1. If you want to test this out for optical transitions, you can take hydrogen, in which the radius r is of the order of 1 angstrom, whereas the wavelength of light, if it's optical radiation, it's about 5,000 angstroms, or if you prefer 500 nanometers. But anyway, you see the ratio of this is like 5,000. By the way, if you took the 2p to 1s transition in hydrogen, which is the fastest of all transitions, this is called the Lyman alpha transition. The Lyman alpha transition, the lambda for that is about 1200 angstroms, or 120 nanometers. This is in the UV range, and you see the ratio is somewhat smaller, but it's still over 1,000. It's actually a good deal bigger than 1 over alpha, which is only 137, and that's because there's factors of 2 and dependence on quantum numbers and so on enter in there to make it even more favorable. But in any case, it's easy to see that the k dot r is not only of order alpha, it's actually even smaller than that. In particular, it's a small quantity. So if we go back to the MBA, then you can see that the first term here, which is p dotted into the polarization vector, is independent of k. This is all of order unity in atomic units. The spin part, on the other hand, has a k in it, which means this term is small in comparison to the first term. Also, the exponent, e to the ikr, the exponent k dot r, is small. And so therefore, it's reasonable to expand this out as 1 plus I times k dot r. And if I do that, then at least through the first lowest order in expansions in the fine structure constant, the p dot epsilon gives us the lowest order term, which is independent of alpha. The spin dot k and then the k dot r, which is multiplied times the p dot epsilon, gives us the next term, which is the first order in k. And so if we do all of that, and I draw some line here on my new page to bring it out, if we do all of that, it means that we can take our matrix element, MBA, and we can write it as a MBA 0, which is of lowest order, plus an MBA 1, which is a first order in alpha, plus higher order terms. So this, of course, is order alpha to the 0. This is alpha to the first power. There's alpha squared terms. There's higher order terms out there like this in the expansion of this matrix element. The MBA 0, to write it out explicitly, is just the p dot a term. So this is equal to bring it back, it's, p dot epsilon term. It's multiplied by I over h bar, and otherwise it's just sandwiched between states B and A. So this is equal to I over h bar times B p dot epsilon in the middle and A on the right. And I'll write this as I over h bar times epsilon hat vector dotted into the matrix elements of the momentum operator between B and A. Epsilon is just a C number. It's the polarization of the outgoing photon. So it's not really an operator. The operator is the momentum. So the MB0 is proportional to the matrix elements between the initial and final atomic states of the momentum operator. The MBA at first order, is going to involve There's an I over epsilon, but the two factors in the middle also involve an I, which gives you an I squared, which is -1. So you get a -1 over h bar, and you get a B on one side, and then you get a P dot epsilon, like this, multiplied times K dot R, which came from expanding the phase factor, e to the I K dot R. And then we get the spin dotted into K cross epsilon. That's from the magnetic moment terms. We get this for the expression at first order in the fine structure constant. Now, it won't do to expand the MBA out to higher order in the fine structure constant alpha squared and beyond, because these amount to higher order, effectively relativistic corrections. And since we're only using the non-relativistic version of the Hamiltonian here, it wouldn't be accurate to carry MBA out that far in expansions in alpha. If we wanted to do that, we'd need to include fine structure terms in here as well, relativistic corrections there. Or probably what's even easier is to use the Dirac equation, which would have something that's nominally to all powers of alpha. In any case, for our purposes tonight, we're going to stop here at the first two terms, which is suitable for a essentially non-relativistic treatment. All right, so the first thing we did to the matrix element was basically expand in powers of the fine structure constant. Let's look at the MBA 0. Atomic physicists don't really like matrix elements of momentum. The reason is momentum is a derivative operator and it's numerically hard to handle. They'd rather have matrix elements of a position operator. Turns out you can convert one into the other. We use the following identity, is that the momentum P divided by the mass is the same thing as 1 over IH bar times the commutator of the position vector with the Hamiltonian H naught, where the H naught here is just the matter part of the H naught P squared over 2m plus V of R. This is really just the Heisenberg equations of motion using H naught as the Hamiltonian. In other words, this is the same thing as R. I call this X vector. I want to call it R. I'm using R vector here for the position of the electron tonight. So let's just call this R vector dot. That's what this is. If the time derivative is computed with respect to H0, this is what we get. In any case, for our purposes, this creates an identity in which the momentum can be written in terms of a commutator of the position operator with respect to the unperturbed Hamiltonian. Now, if I do that, and let's bring this down, then the MBA 0 here becomes I over H bar, and then I have a 1 over H bar, 1 over IH bar from the commutator, and then we've got epsilon dotted into, and we've got B on the left-hand side. That's B, B is a state B, and it's not a vector. And then inside is the commutator, which is R vector H naught minus H naught R vector, like this, and then atomic state A on the right-hand side. Now, having done that, we can then let this H naught act on A under the right, it's atomic state A, that brings out energy E sub A, and let this H naught act on atomic state B on the left, this brings out EB. And the result is you get a factor of EB minus EA. No, sorry, it's the other way around. It's with a positive sign. The term with the positive sign is EA. It's EA minus EB. And that's the same thing as minus H bar times omega BA, where omega BA is the Einstein frequency connecting the initial and final states. However, omega BA is the same thing as the frequency of the photon, so I'll just write it as minus H bar omega, where omega refers to the photon energy. And so including this minus sign and canceling out these I's, and there should have been a mass in here too, because of the, I need to multiply through by the mass here, you see, to get just a formula for P. Then what we get is that this MBA at this order is equal to minus M omega over H bar times the matrix elements between the two atomic states of just the position vector, like this A, like so. We get this formula for the MBA at this order. This is called the electric dipole, or E1, contribution to the matrix element. The reason it is the electric dipole moment operator for the electron is just its charge times its position. And so you can see this matrix element is proportional to the matrix elements of the matrix element of the electric dipole operator. Oh, I forgot, this is dotted into epsilon here, like this. Epsilon's dotted into this in the matrix element. By the way, the epsilon is the direction, it's the polarization vector. So in classical E&M, that's the direction of the electric field. You can see what you've got here is the electric field dotted into the dipole moment of the atom. At least that's the idea of the algebra here, which is of course the energy of the dipole in the field. All right. All right, in any case, this is MBA, and so I'll put an E1 on this to indicate that this is the electric dipole contribution. And then somewhere here, I'm accumulating a summary page of these results. And so here it is. Here's a matrix element summary page. Let me pull this out of the way. Matrix element summary page. Here's the overall matrix element. We expanded it. We expanded it out in powers of alpha. And the leading term is this MBA E1, which I've reproduced down here. Here's the formula for it. Now it turns out there's other contributions too, and I want to come back to that now. All right. Now then, so that's the first part. Now to get the rest of this, then let's go back to an earlier part of the calculation. Here's the MBA 0, which turned into MBA E1. This is electric dipole contribution. Let's now look at the next order correction in powers of alpha. It's a longer, more complicated expression. Here it is. But it has a factor of k in both terms. That's what makes it of order alpha. And there's a p dot epsilon and a k dot r. Let's analyze this term next. So I'll do it down here. In the first place, I want to note that the p dot epsilon factor and the k dot r factor. Okay, so there's two terms here. There's this first term, let me call it 1, and there's a second term 2. The first term involves the p dot epsilon k dot r, and the second one involves the spin. Let's just look at the first term first. I want to point out that these two factors actually commute with each other, because if I compute the commutator of p dot epsilon with k dot r, and you just do commutator algebra and work this out, you get minus I h bar times epsilon hat dotted into k. That's what the commutator gives you. On the other hand, light waves are transverse, and so the polarization vectors are orthogonal to the direction of propagation. And so this is equal to 0 by the transversality of light waves. And that means that I can rearrange these two factors in any order we want. So to talk about the number one part of this matrix element at order alpha, we get it with a minus sign, minus 1 over h bar, and we can write it this way. Let me swap the order of these two and write it in the following form: is ki epsilon j, and then we've got b xi pj a like this. The using a summation convention for contracting the k and epsilon with the x's and the p's. The k and the epsilon are C numbers. They depend only on the mode of the photon, but the x's and p's are operators, so they have to stay inside the matrix elements. Now allow me to take this matrix element and let me symmetrize and antisymmetrize the tensor xipj. So we have one term which is 1/2 of b xipj minus xjpi. That's the antisymmetric part, A. And then we get plus 1/2 of b xipj plus pi plus xjpi A, like this. So let's call this the antisymmetric part and the symmetric part. All right. Now then, the calculation proceeds like this. Let's work on the antisymmetric part first. xipj minus xjpi can also be written as epsilon ijk times the orbital angular momentum L sub k. For example, xpy minus ypx is equal to Lz. You can see how this formula comes about. Now the epsilon ijk, however, can combine with the polarization and wave vectors here to give you a cross product. And the result is that for the antisymmetric part, what we get is we get minus 1 over 2h bar. The factor of 2 came because we divided these things into the two parts. Factor of 2h bar, we get k crossed into epsilon hat is then dotted into the matrix element between B and A of the orbital angular momentum, like so. All right. Now, if you then compare that to, let me go back to the previous page, to the spin part of the matrix element, that's k dot epsilon dotted into the matrix element of the spin times between B and A, although there's no factor of 2. And so if we combine those two together, we get what we call the magnetic monopole contribution. Let me write it this way: is MBA M1. The M1 means magnetic dipole. And this becomes minus 1 over 2 H bar times K hat crossed into epsilon hat dotted into the matrix element between B and A of L plus twice S. A like this. No sign in A, no vector sign in A. There we go. This is the magnetic dipole, or M1 contribution to the matrix element. You can see that it's a magnetic phenomenon because, again, in classical E&M, the polarization vector is in the direction of the electric field. K crossed into that gives you the direction of the magnetic field. So what you're getting here is a magnetic field dotted into an expectation value of what? It's L plus 2S. Well, it's not just L plus S. That would be the angular momentum of the electron, total angular momentum. It's L plus 2S. And the 2 here is really the G factor of the electron. So what's appearing here is something that's proportional to the magnetic moment, or the average magnetic moment essentially between the two atomic states of the electron, orbital plus spin combined together with the right G factor. So this whole thing has the structure of a mu dot B term, you see, and that's an indication this is the magnetic contribution. So if I can go back to my summary sheet then, here it is. There's a second term in the expansion of this matrix element, which is the magnetic dipole term, and it's given explicitly. Here's the formula for it. It's the same formula I wrote down earlier. Involves L plus 2S between the initial and final states. Now there remains then one more term in this analysis, and that is where is it here? And that is, if I can find, not this one, no. Here, excuse me. That remaining term is the symmetric part right there. The symmetric part of the number one matrix element. Let's analyze that. So for the symmetric part, that's going to be minus 1 over 2 H bar, just to spell it out explicitly, minus 1 over 2 H bar, Ki epsilon J, and then B and A sandwiched around Xi Pj plus Xj Pi, atomic state A on the other side. Now the first thing I'm going to do is to swap these two factors to turn into Pixj, which I can do because K dot epsilon is 0. If you work out the commutator is 0, and that's legitimate to do. Then next what I'm going to do is use the same atomic physics trick as before, which is that P sub I is equal to M over IH bar times the commutator of X sub I with the unperturbed Hamiltonian H0. And if I do that, let me get some space here. And if I do that, then what we get is, let me make sure I'm on the screen here. In fact, let me do this. I think the screen might look better if I redo this. Okay, I hope that's better. So if I do that, then I substitute in this Pi over the Pj in that position there and that position there. And what we're going to get for the symmetric part then is equal to minus 1 over 2 H bar, Ki epsilon J. Then we have B like this. We've got Xi, oh, and then there's a factor that goes in here is M over IH bar, which came from the commutator up here, you see. And there's the Xi Pj. This is going to be the commutator Xj with H0. And then we have plus here the commutator of Xi with H0 times Xj. And then that's A on that side here like this. And if we look at this matrix element, this becomes B, Xi, Xj, H, just expanding out the commutators, now this one and that one, Xi, Xj, H0 minus Xi, H0, Xj for the first term. For the second term, I get plus Xi, H0, Xj minus H0, Xi, Xj, A, like that. And if we do this, we see these two middle terms cancel. And this H0 acts on that A over there to give us an EA, and this H0 acts under this state B over there to give us an EB. And so once again, we get an EA minus EB, which just as before is equal to minus H bar omega. And so if I put this together, I get minus 1 over 2 H bar, factor there. I get M over I H bar. I get minus H bar omega, like this. Those are the prefactors. And then what's left over is Ki epsilon J, matrix element B, and A between the operators Xi, Xj. You can start to see the appearance here of a quadrupole moment tensor that's appearing here. It's the second moment of the charge distribution is the idea. All right, so these prefactors here, minus signs cancel, get another minus sign. This is equal to minus I M omega divided by H bar, 2H bar, there's a 2 in there, Ki epsilon J. And now what I'm going to do is divide by 3 and put a B here, this atomic state on the left, and I'll put a 3 Xi Xj in there. I multiply and divide by 3, so that cancels, gives me what I had. But now I'm going to subtract off delta ij r squared and the state A like that on the right-hand side. So I added in a new term here, or subtracted it. Now, why did I do that? In the first place, to point out this new term is actually 0, because the Kronecker delta ij gives me the contraction of k with epsilon, which is 0 because of the transversality of the light waves. So this extra term didn't do anything in terms of changing the answer. What it did do is it made this operator, which appears in the middle, it made it a rank 2, k equals 2, irreducible tensor operator. It's the quadrupole moment tensor in the manner in which we defined it earlier last semester. It's what I call Qij. And so what we get then is we then get the electric quadrupole contribution to the matrix element. And I think instead of writing it out, I'll just switch to the summary sheet and show you where it appears here. Here it is in the summary sheet. It's the third term in the expansion of MBA. Electric dipole, magnetic dipole, electric quadrupole. Here's the first two, and here's the new one we just derived. Here's the electric quadrupole matrix element. It's the quadrupole moment tensor sandwiched between the two atomic states, contracted with a wave vector and the polarization vector on the two sides, where Qij is defined this way. This is the quadrupole moment tensor. All right. Now then, so that involves then a breakdown of the matrix element MBA that came from this simple application of QED. And we've done two things here, some algebra, but we've done two things. The first is to expand the matrix elements in powers of the fine structure constant. One of the consequences of that was that we found that this phase factor, e to the IKR, is actually nearly constant over the dimensions of the atom. We took into account the first correction term by expanding this out to first order. That's what gave us the combination of the M1 and E2, or actually it contributed to the E2 as a matter of fact, what it did. But in any case, we took into account the first order corrections. But as an approximation, the basic fact here is that the phase of the light wave, which is what this thing is nearly constant over the extent of the atom. That's obvious if you think about the size of the atom versus the wavelength of the light. And at least for ordinary atoms and ordinary optical transitions, that's clearly true if you just know the numbers. Of course, this wouldn't necessarily be true in all applications. And in fact, in other applications, like in particle physics or nuclear physics, it isn't always necessarily so true. And you may need to take into account the actual oscillations of the e to the IKR over the extent of the atom. This starts to touch on a number of aspects of what you might call antenna theory that you can learn about in classical E&M, but these aspects reappear in this problem because, of course, the atom really is a little antenna which is radiating light waves when it emits a photon, and we're treating it quantum mechanically, but many of the ideas carry through. All right. In any case, in this approximation that we're making here, or this system we're analyzing, it's a good approximation to expand this out. By the way, to replace this exponential factor simply by 1, just to drop it, is sometimes called the dipole approximation, quote unquote, or the electric dipole approximation, because if you do that, and if you neglect the spin term also, which is also small, then you just get the leading order term here, which is the electric dipole contribution. So that's useful terminology. It's called the electric dipole approximation. It's used in many applications. Now, the total matrix element, which has to be squared to get the transition rate, is really the sum of all these things and plus others that we didn't calculate. And so and these are complex amplitudes, and when you square them, of course, you're going to get cross terms. So the cross terms are there are interferences between the different terms, and of course, they will contribute to the transition amplitude. Nevertheless, as we will see, it turns out that in a typical application, many of these various terms that these three terms that I've listed here, it often happens that some or many of them vanish on account of selection rules. It depends on the initial and final states, which carry certain symmetry labels. And if they do, then there's some leading term, which is in the dominant term, because the higher order terms are higher order than the fine structure constant. Let me remind you that this term is of order, the dipole term is of order alpha to the 0, where these other terms are of order alpha to the first power. That is to say, they contain a factor of k in them. So these two are the same order of magnitude, but typically one or the other of them will vanish because of selection rules. So you've got some leading term and then higher order corrections in alpha in the fine structure constant. And so as a result, we speak of, if the E1 were the leading term, the first term, which is non-zero, we would speak of electric dipole radiation. But if that term were 0, but the M1 term were non-zero, then we'd speak of magnetic dipole radiation, and similarly for E2 and so on down the line. All right, now then, so that's the analysis that I want to make of the matrix element. Let's see, the next thing to talk about is, actually, I do want to say more about the matrix elements. You can see that these matrix elements, all three of them, involve matrix elements between the initial and final atomic states of certain operators. There's the position operator, there's L+2s, and then there's the quadrupole moment tensor. And all three of these operators are actually irreducible tensor operators. So now you start to see some playground for the application of the Wigner-Eckhart theorem. These are exactly where the Wigner-Eckhart theorem is useful. Matrix elements of atomic states between irreducible tensor operators. So allow me to address that question here. I'll do this by setting up a table. Let's talk about the pole. There's going to be a long table here. Let's talk about the pole. So we have the electric dipole, the magnetic dipole, and the electric quadrupole. These are the three that we talked about. We have an operator which is in the middle, and that operator is an example of an irreducible tensor operator. So it's like a TKQ. So for the E1, it's the position operator R. For the M1, it's L+2s, the angular momentum. Really, the magnetic moment is what it is. And for E2, it's the quadrupole moment operator, QIJ. And these have K values, which is 1 for vector operators, because vector operators are always K = 1 irreducible tensor operators. Let me clear some of this out of the way. And move this up. In fact, let me rip it off and adjust it. This is a table I want to produce. So these are K = 1 irreducible tensor operators, whereas the quadrupole moment is a K = 2 operator. These operators also have certain transformation properties under parity. The position vector, of course, is odd under parity, if you remember parity from last semester. Also, if you remember that angular momenta are even under parity, so L+2s is even. The quadrupole moment tensor is quadratic in the position, so there's like two minus signs which make a plus. And so these have parities which are odd, even, and even running down the table. Now then, they also have order in alpha, which I've also listed before. This is alpha to the 0 for the electric dipole, alpha to the first, and alpha to the first power for the other two. Now then, this leads to selection rules. So in the first place, let's suppose in our looking at our atom here in the upper state and the lower state B and A, this is if it's a central force problem, we can write the eigenstates with their central field quantum numbers, NLJ, MJ, let's say for the upper state, and NLJ, MJ for the lower state. We'll put primes in the lower state like this. Let's suppose we have that situation. then we've got, then the Wigner-Eckardt theorem, you see, can be applied to the matrix elements between states B and A using the total angular momentum J. These K values here relate to how these operators transform under total rotations of the system, orbital plus spin. That's where these K numbers came from. So by the Wigner-Eckardt theorem, we find, for example, that the delta J here, for this case where we've got a K equals 1 operator in the middle, has to be either equal to 0 or plus or minus 1. The same thing is true for the M1 transition. Delta J is equal to 0 or plus or minus 1, again, because it's a vector operator. The E2 operator, electric quadrupole, is a K equals 2 operator. So now J can change by 2, so the delta J's are 0, plus or minus 1, or plus or minus 2. That's what you get for the delta J values. Now, on the other hand, these states are also eigenstates of orbital angular momentum, L, and L prime, as you see here, like this. So we can also apply the Wigner-Eckardt theorem using just purely spatial rotations. If we do this for the position vector r like this, then this r is a purely orbital operator, spatial operator. So it's also a K equals 1 operator in a purely spatial rotations. So as far as the Wigner-Eckardt theorem is concerned, we get delta L is equal to 0 and plus and minus 1, the same that we got for the J. However, as we know from last semester, the parity excludes the delta L equals 0. It means the states have to be A and B have to be opposite parity. So the delta L has to be odd, and so we only get a delta L equals plus and minus 1. And these then are the usual selection rules for electric dipole transitions. For the magnetic dipole, however, the operator in question is even under parity, not odd. And so that excludes the odd values of delta L. And so the magnetic dipole will vanish unless delta L equals 0. That's the only even choice. Now, the E2, the Qij, is a K equals 2 irreducible tensor operator under both under both rotations generated by J and also those generated by L. So it's a K equals 2 operator for under L rotations as well. And so as far as Wigner-Eckardt is concerned, that would give you delta L is equal to 0, plus and minus 1, or plus or minus 2, just like we see with the J values. However, since it's even under parity, it means the delta L has to be even. And so the only delta L's that are allowed are delta L equals 0 or plus or minus 2. Plus or minus 1 is not allowed. And so these then we get these different selection. So these are different selection rules you see for the different multipole transitions. And this is why typically some of these vanish and others are, some are 0 and some are non-zero, depending on the initial and final states B and A, what the quantum numbers are. All right. Now then, this leads to some interesting features. By the way, there are some other selection rules too that are really not part of the table yet. Here's an example of this. If I have a J equals 1/2, I'm talking about a single electron atom, so the J is half integer. If we talk about a J equals 1/2 making a transition to a J equals 1/2, this is impossible with an E2. With an E2, this will not go. And the reason is because the E2, the K is equal to 2, you see. And if I combine 2 crossed with 1/2, the thing is I don't get a 1/2 coming out of it. 2 crossed with 1/2 gives me a 3/2 plus a 5/2. You don't get a 1/2. So it's impossible to reach 1/2 by having a K equals 2, and therefore the matrix elements vanish. In the case of a single electron atom, we only have half integer J. There's no other choice because the spin is half integer. If you had an atom that has an even number of electrons, more than one, an even number, like 2, like helium, for example, then the total J is even. And there's similar selection rules there's similar selection rules that arise in this case. For example, a J equals 0 goes to J equals 0 is not allowed for either an electric dipole or a magnetic dipole transition. And the reason is that 1 crossed with 0 does not equal 0. You can't reach 0 by crossing 1 with 0, you see. Actually, this applies also to 2 crossed with 0 and so on. This is also not equal to 0. A J equals 0 to a J equals 0, in fact, is forbidden for all the multipoles going all the way on out. it's what sometimes this is called strictly forbidden, meaning that it vanishes for all the multipole moments. Does that mean the transition doesn't happen? No, actually, it may happen, and I'll say something about that in a minute. In fact, let me say some things about that. Let's talk about, as long as we're talking about transitions, let's talk about hydrogen. We have a 1s level down here. Up here is a 2s and a 2p. Then we have a 3s, a 3p, and a 3d, like this. So electric dipole transitions involve delta L equals plus or minus 1. So you get this, for example, you get that, you get that, you get this. These are all examples of transitions that are allowed as electric dipole. If I made the diagram going on up like this and drew in all the arrows, you get a kind of an image of a pinball machine. If you had various excited states, they would make electric dipole transitions rattling all down. And if you wait after a while, what would be left is only two states. One would be the ground state and the other would be the 2s state. Because if you get in the 2s state, you cannot make a transition to the ground state using electric dipole because that's delta L equals 0. So in other words, you get a mixture of the ground state plus this 2s excited state. That's what happens after a while. What about other transitions? How about electric quadrupole? Electric quadrupole could take you from a 3D to a 1s. That's possible as an E2 because that's a delta L equals 2, you see. It could not take you from a 3p to a 1s or a 2p to 1s. That wouldn't work because delta L equals 1 is not allowed for electric quadrupole. There's a good deal of curiosity attached to the 2s state because it's metastable. You see, it doesn't make a transition either by electric dipole or by electric quadrupole. What about magnetic dipole? Magnetic dipole would seem to work because delta L equals 0 is the selection rule there, and this is a delta L equals 0 term. But if you analyze it in a little more detail, you find the matrix element is 0 because the radial wave functions are orthogonal to one another. They're both S waves, and the 1s radial wave function and the 2s radial wave function are the same. And so you look at the matrix element, you'll see this vanishes. And so the M1 transition doesn't work either, not because of these selection rules up here that have to do with angular momentum, but because of radial matrix elements. So this enhances the question even further, interest in the question about what really does happen if the atom finds itself, if hydrogen finds itself in the 2s state, which it will easily. How does that happen? I mean, not how does it happen, but rather what happens if it does? Okay. So the overall analysis of this transition, 2s to 1s, is actually rather complicated. In particular, the M1 transition, which, as I just explained, is being forbidden, is a little more complicated than I presented it. It's because the vanishing of that radial matrix element is only holds in the Schrödinger-Pauli theory. If you model a hydrogen atom in the Dirac theory, you find that there actually is a non-zero radial matrix element, but it's higher order in the fine structure constant than you would have expected. This is not something you can get out of the Schrödinger-Pauli theory. And the result is that the M1 transition actually can occur from 2s to 1s, but it's very slow. And in fact, it's not the dominant mechanism at all. The dominant mechanism, in fact, is a two-photon emission involving two E1 transitions, but two photons. It's a two-photon transition. By the way, not only is the E2 not allowed, none of the higher multipoles are allowed either. Again, because you can't reach 1/2. It's this 1/2. It's this thing up here is that you can't reach 1/2 goes to 1/2 with a k equals 2. So the electric quadrupole doesn't do it either, and neither do any of the higher multipoles. The dominant mechanism, as I say, is two-photon emission. This two-photon emission is much slower than the electric dipole transition from the 2p to 1s. The 2p to 1s transition has a lifetime of about 10 to the minus 9 seconds. In fact, this is the most rapid transition in hydrogen. It's called the Lyman alpha, which I think I mentioned earlier. This is an ultraviolet photon with a 120 nanometer wavelength of the photon, like this. It's very important in astrophysics. Whereas the lifetime for the direct transition from 2s to 1s is about 10 to the minus 1 seconds. It's about 100 million times longer because of selection rules, even though the initial states have exactly this, are very close to the same energy and so the energy of the transition is the same, essentially the same for both these transitions. but they have very different lifetimes. All right. So that's the breakdown of the matrix element into multipoles and some analysis of that. Are there any questions about that? All right. If not, then I shall turn to the next topic, which is the next topic is to play more games with spontaneous emission. Spontaneous emission is the most fun part of this business. It's the part that could not be, as I said, could not be obtained by. Let me get my formulas here. Could not be obtained by the semi-classical theory of radiation. Here's my summary sheet from Tuesday night's lecture, repeated again, brought back again. Here is a differential transition rate which involved the matrix element squared. We've been doing a lot of analysis of MBA now. Here it is. We broke it up into 3 terms going in there. Let's take a look now at the total transition rate. That's to say the Einstein A coefficient. Let's work on calculating that. The main effort here is to calculate the polarization and angle average of the square of the matrix element. So what I'd like to do is to begin with the dominant term, which is the electric dipole term for the MBA, which we just worked out. Plug that in here, do the angle and polarization average, and then end up getting a useful formula for the Einstein A coefficient in the case of electric dipole transition. So let's do that now. So here's going to be the plan then, is to copy the formula. We've got the Einstein A coefficient AE is equal to 4e squared over m squared c cubed times m squared c cubed times h bar omega times the MBA squared and averaged. And the MBA squared and averaged, the MBA we're going to replace by MBA E1. And that's equal to, if I use my other summary sheet over here, it's equal to minus m omega over h bar times epsilon hat dotted into the matrix elements of the position operator. I'll call it R here for the position operator. A like that. Okay. And so let's plug this in. So let's carry out the square. We'll square it and we'll average it and see what we get. Let's work on that first. So MBA squared. So here's what we want. Is we want first of all MBA squared, absolute value squared. This is going to be equal to m squared omega squared over h bar squared times the absolute value of epsilon hat times the absolute value of epsilon hat dotted into the matrix element B R A like that squared. And then in order to compute the average of this, we need to average this thing. So we want to take this and average it to replace it by 1 over 4 pi integral over solid angles 1/2 the sum over polarizations of this thing epsilon hat dotted into B R A like this squared. All right, that's what we like to evaluate. All right, put this away. So let's do it like this. Get the paper right. Let me press this thing to kind of focus it again. I think it got out of focus. All right, I hope that's an improvement. All right, now here's what we're going to do. This epsilon it's a polarization vector, so it depends on mu, and so the sum here is running over the polarization vector. Let's call this BRA thing. Let's just define this to be R vector BA. It's just a shorthand for that matrix element. It's the matrix element of the position operator between the 2 atomic states. The wave functions for these 2 atomic states may be complex, so this is really a three vector, which is a complex vector in general, worthwhile keeping in mind. In any case, this sum on mu of this matrix element squared, if I bring it down onto my next piece of paper here, I can write this as a sum on mu of RBA complex conjugate dotted into epsilon mu complex conjugate times epsilon mu dotted into RBA. And we can do the polarization sum because you see you've got a sum over something that's starting to look like a resolution of the identity. Here's the resolution of the identity, epsilon mu of, sum on mu of epsilon mu star times epsilon mu. This runs only over the transverse polarization vectors, but if I add the longitudinal polarization vectors k hat, I get a resolution of the identity in three-dimensional space. And so solving for this term and plugging in there, it's going to be identity minus kk. And the result is this turns into RBA vector absolute value squared minus k hat dotted into RBA vector squared. And so this average of this thing squared over polarizations turns into this. So this means that MBA squared averaged is equal to m squared omega squared over h bar squared. That's copying this prefactor up here. And then what I've got is 1 over 8 pi. The 8 pi came from the 1/2 and the 4 pi here. That's in the normalization of the averaging. I still have the solid angle d omega integral still has to be done. And then we've got RBA absolute value squared minus k hat dotted into RBA absolute value squared. Now this omega is the direction of k. It's the direction of the outgoing photon. The first factor is independent of k. So in this integral, the first thing we get is just 4 pi times the absolute value of RBA squared, like that. As far as the second factor is concerned, we just have one component of RBA square of RBA quantity squared, and that component, again, I'm going to try to see if I can brighten up the screen a little bit. Good. And so the average of one component of a vector squared, if you think about the z component in ordinary three-dimensional space, that gives you a cosine theta times r. So z squared, if I average this, it's the average of cosine squared theta times r squared. But the average of cosine squared theta over the sphere is 1/3. And so this turns into a minus 4 pi over 3 times the same RBA vector squared. It's possible to do this angle averaging without too much trouble, and this is what you get when you do it. So 4 pi minus 4 pi over 3 is the same thing as 8 pi over 3. The 8 pi denominator cancels, and this thing turns into, bring it down here, this thing turns into, finally, 1/3 of m squared omega squared over h bar squared times the absolute value of RBA squared. All right, so that's the square of the matrix element, MBA squared. Now then, let's work on RBA squared. Let's have the states B and A here. And let's say that this has quantum numbers NLJ, MJ for our single electron atom, and this has quantum numbers NLJ, MJ with primes on them for the lower state like this. So here's what I'm going to do. I'm going to take RBA squared, its absolute value squared. I'm going to write it as RAB squared. This is a trick which you learn by doing it the hard way first. RAB is just the matrix elements between states A and B in the right and left-hand side instead of states B and A. But that's equal to RBA complex conjugated because R is a Hermitian operator. So I can write this in either order, and the AB form is more convenient. So let's take that then. So then here's what we want to do is we want to take RAB, which is equal to A and B sandwiched around the vector R. And the trick here is to take the position operator R and to expand it as a linear combination of the spherical basis vectors that we talked about last semester. They come in complex conjugated form with coefficients I'll call x sub q. where x sub q is equal to E hat q dotted into the position vector r. The x sub q is just the components of the position vector r with respect to the spherical basis, or rather with its complex conjugate. And this is the same expansion that we dealt with last semester. So this means that RAB now can be written this way as a sum on Q of E hat Q star with A and then X sub Q in the middle and then B on the right. Now this is convenient because the X sub Q, when we worked this out last semester, can be written as the square root of 4 pi over 3 times the radius vector R times y1q, the spherical harmonic of theta and phi. And I'm afraid this is running off the screen and you can't see it, but that's what this is. The reason for doing this, switching to the spherical basis, is the components of the position vector in the spherical basis are proportional to YLMs. So what this turns into then is that RAB squared, RBA squared, which is the same thing as RAB squared, turns into this, the absolute value of the sum on Q of E hat sub Q, complex conjugated, A on the left, XQ in the middle, and B on the right, squared. Okay? But the E hat sub Q's are an orthonormal basis. And if you want to square a vector whose components in an orthonormal basis are given, you just sum up the squares of the components. So this is just equal to the sum on Q of the absolute value of the components squared, like that. So now we're reduced to evaluating this matrix element, and let's work on that. This is the same thing as, to write it out explicitly, it's oh, you know what I want to do here? Let's simplify the model at this point. At this point, I'm going to simplify the model. Here's the upper state and here's the lower state. Instead of taking a model that includes the spin, as I did here with these quantum numbers NLJ, MJ, for the sake of simplifying this calculation, allow me just to use an electrostatic model for this, NLM in the upper state and NLM with primes on them in the lower state, like that. Let's suppose we do that. Here's the photon that gets emitted. So if we do that, then this matrix element is equal to N prime, L prime, M prime on the left. The X sub Q is the square root of 4 pi over 3 times the radius times Y1Q. And then we have NLM on the right. And you can write this out, if you write this out as a matrix element doing the integral, you can write it out as a product of a radial integral times an angular integral. I actually went over this last semester, so I'm repeating some stuff I've done already. Is that this becomes equal to, let's call it a radial integral times an angular integral. And the radial integral is equal to the integral from 0 to infinity of r squared dr. The radial wave function for the state on the left, that's r n prime L prime of r. There's a factor of r in the middle. And then there's a radial wave function for the cat on the right, r like that. And then the rest of it, what's left over, is the angular integral. I'll take this factor of root 4 pi over 3 for the angular integral. Then we get an integral over solid angles. Over here, we get a YLM with prime values, YL prime, M prime, and that's complex conjugate, theta and phi. In the middle, we get a Y1Q of theta and phi. And on the right, we get a YLM of theta and phi. So you see an application here of the 3YLM formula, which we worked out last semester. And to remind you of that, here it is. Here's the 3YLM formula. Here the notation is a little different. There's L3, M3 has got the star on it, and L1, M1, L2, M2 have no stars, but you've got the square root factors and the product of two Clebsch-Gordon coefficients. And what this means is that this I omega can be written, if you apply the YLM formula, you get this. You get the square root of 2L plus 1 divided by 2L prime plus 1. you get a Clebsch-Gordon coefficient, L prime, M prime, and then you get L1 MQ. And then you get another Clebsch-Gordon coefficient, L1 0 0 times L prime 0, like this. You get those. All right. And so now we can put this together and get RBA squared. And that's equal to, so I need to square, running through all this. So there's going to be a sum on Q. It's the square of this matrix element AB, which I just worked out here. So there's the sum on Q. There's this thing squared, 2L plus 1 divided by 2L prime plus 1. I get the square of these Clebsch-Gordon coefficients. I'll fill that in later. And that's the RBA, that's the RBA squared. Okay. Now, to go back and put this all together then, if I can do it right, I mean,
sorry, where did the radial integral go?
It disappeared. It should be in here, and it should be times an IR squared. Let me put it in here, IR squared. Thank you. I hope I didn't omit anything else, but it needs to be in there. All right. All right, now then. So then to go back, the Einstein A coefficient, A for an E1 transition, is equal to 4E squared over M squared C cubed. And then we had a 1/3, and I need to look back in my notes to see what the formula was. I can find it here. Yes, it's M squared omega squared divided by H bar squared. And then what's left over should be the RBA squared. I'm going to leave a little space here. I'm going to put a sum on Q here. And then we've got the radial integral IR squared. That's independent of Q. And then we've got the square of the matrix elements. So let me write them out. Let me write this way as L prime M prime L1 MQ times L1 MQ L prime M prime. And then that has to be multiplied by the square of the final matrix element, which is L prime 0 L1 0 0 squared. Okay, hope I did that right. Okay, now this is the transition. This is the spontaneous transition rate between one specific between this B state and this A state up here. But the B state is degenerate because the energy doesn't depend on the magnetic quantum number. And the same thing's true for the A state where it's an M prime. So let me bring this over so you can see better. Now, in many practical circumstances, we don't actually know what the magnetic substate is of the excited state. A common case in practice is one in which the excited state is isotropic, as to say it has no spatial orientation, statistically speaking. And that's equivalent to saying that all the initial M magnetic substates are equally probable. Likewise, when the atom makes a transition to the lower state, there's nothing to prevent it from making a transition to any of the M prime states that it wants to. In fact, that's exactly what it'll do. And so the spectral line that you see is going to be a sum, or the intensity you'll see will be the sum of the intensities of the transitions from any of these initial states to all of the final states. And so to get the effective transition rate, or in other words, to get something that gives you the intensity of the spectral line that you would observe experimentally, it's necessary to average over the initial states and to sum over the final states. In fact, this is kind of a mantra in this business of doing transitions or scattering theories. You average over initial states and sum over final states, unless you're dealing with polarized beams and so on, which is a more detailed situation. In any case, to go to my formula down here, if we average over initial states and sum over final states, then what I need to do is to insert in here the average over the initial states is going to be a sum. Here's the initial states. It's the magnets is 1 over 2L plus 1. And then it's going to be a sum on the magnetic quantum number M. And then to sum over final states, I sum over magnetic quantum numbers m prime in the final state. So let's take this and insert that in there. And by the way, I omitted a factor here because I didn't copy it right, which is this 2L plus 1 over 2L prime plus 1, which came out of the calculation. Let's put that in there also. Now you can see that if I do that, the 2L plus 1 factor in the denominator and the one in the numerator cancel. Also, I'm summing over Q there, and I'm summing over M there. But right here, summing over M and Q gives me a resolution of the identity. And so that's just going to turn into 1 as an operator. And that'll take care of the Q sum and the M sum, leaving behind the M prime sum. However, this also leaves behind the scalar product of L prime M prime with itself, which is equal to 1. And the result is the M prime sum is now summing something that's independent of M prime. So it just ends up multiplying it by 2L prime plus 1, which is the number of possible values of M prime. But what that does is it takes care of the M prime sum and takes care of the M prime sum and cancels the 2L prime plus 1 in the denominator. And so if we do this and we get AE1 effective is equal to 4E squared over M squared C cubed times 1/3 M squared omega squared over H bar squared, copying these factors like this. We then get the radial integral IR squared. These factors went away, those factors went away, and I just now have the square of the Clebsch-Gordan coefficient L prime 0, L1 0, 0, absolute value squared. And this then is the formula that would be usually quoted in books and tables. I can clean this up a little bit, these constants, but this is the formula which is usually quoted in books and tables for the effective electric dipole transition between two states of a single electron atom using the electrostatic model for the states. And this is the derivation of it. So I see that this derivation ends up with leaving me no time left. If you don't mind, let me take at least 30 seconds to just say where I'd like to go with this next if I had time. And that is to explore this formula in terms of how it's related to basically antenna theory, how it's related to the things that we know about classical E&M radiating from antennas. Antenna theory is, there are sort of two cases. There's the case of a small antenna and a case of a big antenna. An antenna is considered small if the size of the antenna is small compared to the wavelength. That's the easiest case. And that's what we have here because the atom is very small compared to the wavelength of the light that's being emitted. This means that the phase of the light wave across the antenna is nearly constant. As I explained earlier, that in fact, that variation is ignored in the electric dipole transition. So that's one aspect of it. Another aspect of this has to do with the relative intensities that come from higher order multipoles, electric quadrupole and so on is down by a factor of alpha squared. I didn't say much about this in timescales and so on, but in any case, there's a lot of interesting things that can be done here, and just by using rather simple considerations, using the electromagnetic Larmor formula, for example, which is classical, you can understand many of the features of this final answer. And if you know what you're doing, it's easy enough to modify it in order to get the rate of emission of gravitational waves from a dipole such as two coalescing black holes. And it's not at all difficult to derive a formula for the envelope. Perhaps you've seen them. If you've seen these results from LIGO and so on, you've seen the chirps that are produced when the black holes merge. It's fairly easy to get an explicit formula for the envelope of that chirp using simple dipole small antenna formulas for radiation. A basic feature that's going on here is that a basic fact that's going on here is that electromagnetic radiation is at lowest order is dipole, whereas gravitational radiation at lowest order is quadrupole. Whereas sound waves at lowest order are monopole radiation, and that's something that's even is even more efficient in terms of radiating. So you can deal with monopole, dipole, and quadrupole radiation in these three different physical effects. Okay, that's all for tonight. Let me ask if there's any questions. I think I'll stop screen share in the meantime. Any questions, please?
Uh, I think I'm confusing myself a little bit. Why do we not need an L sum for a resolution of the identity in the middle there?
Because these are Clebsch-Gordon coefficients, and if you think about how they're used, the L and the one they specify the subspace on which you're doing the combination of the angular momenta.
Oh, yeah. Okay.
Yeah, so this is, you're right, this is a restricted sum, but it's a sum that applies for Clebsch-Gordon coefficients.
Okay, cool. Thank you.
Yeah, basically, this is the orthonormality relations of the Clebsch-Gordon coefficients if you want to look at it from another standpoint. Yeah, are there any other questions? All right. If no other questions, then I shall, as I said a minute ago, stop screen share, and I shall stop